We're now going to talk about the concepts of heat capacity, specific heat, and calorimetry. That's the method with which we can measure the specific heat. So this is how we define heat capacity. It is the amount of energy needed to raise the temperature of a system by 1 degree Celsius. So we have to be clear about the distinction between heat capacity and specific heat. So heat capacity, it's shown with capital C. Heat capacity is capital C. Its unit is calories per Kelvin or calories per degree Celsius. We can also express it this way. And this is the amount of energy that we needed to raise the temperature of a system by 1 degree Celsius. So that's the heat capacity of the system. So it's the amount of heat I have to provide to the system so that it's going to cause an increase in its temperature, delta T. Okay. Now, when we talk about specific heat, it's the heat capacity per unit mass. Specific heat we show it with lowercase c. It's calories per kilogram degrees Celsius. For example, that's the unit. It is the heat capacity per unit mass. So that the total amount of energy I have to provide to raise the temperature by an amount delta T, Q is equal to mc delta T, where the heat capacity is equal to m times C. So I have the energy I have to provide in order to raise the temperature by delta T given in units of specific heat. Now, in general, the specific heat can be temperature dependent. So if you need to take into account the temperature dependence of specific heat, it has a significant temperature dependence, then the energy that we have to provide to raise the temperature by amount delta T will be found from an integral T initial to T final C of T dt. So that the specific heat for a very small temperature change, the variation in specific heat is negligible, so I can use this integral. However, in this course we shall neglect the temperature dependence of T of C, so that we will take C to be a constant for a given system. Another important point here is that the specific heat or heat capacity C is a positive number, so that when I have Q, heat absorbed by the system greater than 0, implies delta T will be greater than 0. What does that mean? Adding heat, absorbing heat by the system, or adding heat to the system, causes its temperature, the temperature of the system, to increase. It's going to increase by a certain amount. Now there is a method for measuring specific heat. It's called calorimetry. And in calorimetry we have the following. We take a vessel containing water. So this is filled with water, and it's cold. And let's say that I have a hot object whose specific heat I'm trying to measure. So this is object X. It's a hot object. So basically I note that this is hot object and this is cold water. And if you put a hot object into the cold water, what will happen is that heat will flow from the hot object to the cold water, so that the temperature of the hot object will decrease, the temperature of the cold water will increase. And this object I call object X. So before I put it into this water, I have measured its initial temperature. For object X, I have initially temperature Tx, and I know its mass, and mass is m sub x. I'm trying to find out what is its specific heat. So when I put it into cold water, the heat absorbed by the cold water will be equal to minus the heat absorbed by the hot object, because the hot object is releasing heat. So that will imply mass of the water. So this water has water mass mW, initial temperature is Tw. So I have mass of water, specific heat of water. When the system reaches the equilibrium temperature, it's going to have the equilibrium temperature T final. So it's T final minus initial temperature of the water, Tw. This will be minus the heat absorbed by the hot object, mass of the object, specific heat of the object, T final minus Tx. Since T final will be less than Tx, this will turn into a positive quantity with the minus sign. So I can use this equation to get, so let me do it here, so that I will have the specific heat of the object is given by a minus mass of the water, specific heat of the water, T final minus T water, divided by mass of the object, T final minus initial temperature of the object. So this is going to tell me what the specific heat of the object is. So I can measure it using this technique, and this is known as calorimetry. Now I want to look at a few examples. A 0.05 kilogram ingot of metal is heated to 200 degrees C. So let me note here, mass of my metal is 0.05 kilograms. Its temperature of the metal ingot is 200 degrees C, and then dropped into a calorimeter containing 0.4 kilogram of water. So mass of the water, MW, will be 0.4 kilograms. Initially at temperature, so T water will be 20 degrees C. The final equilibrium temperature of the system is 22.4 degrees C. Find the specific heat of the metal. So I want to know what is the specific heat of the metal. Again, I have the same setup here, the calorimeter setup. So in this case, X is the metal and water is the cold object. So I have the heat absorbed by the cold object is minus the heat absorbed by the hot object. So what is the heat absorbed by the cold object? The cold object here is water. So it's going to be mass of the water, specific heat of the water, T final minus T water. That's minus mass of the metal, specific heat of the metal, T final minus initial temperature of the metal. So for this I can substitute mass of the water is 0.4 kilograms, and for specific heat of water I have I can take the number from a table or something, but this number is actually very well known. The specific heat of water is it's going to be 1 calorie per kilogram degrees Celsius. So if I use this number, it's going to be 0.4 times 1 times T final is 22.4, T initial for water is 20 degrees C. So that's Q cold. This is going to be equal to minus mass of the metal 0.05, specific heat of the metal I'm trying to calculate 22.4 minus 200 degrees C. So I can calculate the specific heat of the metal here. It's going to be 0.96 divided by 8.88 if you do this calculation, and you can find the specific heat of the metal to be 0.108 calories per kilogram degrees Celsius. So we were able to measure the specific heat of the metal by using the calorimetry technique here. So this is one demonstration of this measurement. Another example, a cowboy fires a silver bullet with a muzzle speed of 200 meters per second into the pine wall of a saloon. Assume all the internal energy generated by the impact remains with the bullet. What is the temperature change of the bullet? So I have initial velocity 200 meters per second. You can look up specific heat of silver from a table in the book. These values are tabulated. It is given as 234 joules per kilogram degrees Celsius. Now this kinetic energy of the bullet, 1/2 mv square, will be transformed into internal energy, so it will cause heating. So it will be equal to the heat absorbed by the bullet. So it's going to be mc delta T. M's will cancel. So I will find that the change in temperature will be V squared divided by 2C. So this will be 200 squared divided by 2 times 234, and this is going to give me 85.3 degrees C. So I find that when all the kinetic energy is converted into internal energy of the bullet by heating, right? So because of the temperature increase, I find that the internal energy of the bullet will increase because the translational, rotational, and vibrational kinetic energies of the atoms and molecules that make up the bullet will increase. However, there is something important to note here. In fact, this is an overestimation. Some of this energy would be absorbed by the wall. So it would go to increase in the temperature of the wall as well. So you wouldn't see such a high temperature change in the bullet. So there is an oversimplification here. Assume that all the internal energy generated by the impact remains with the bullet. So this is an oversimplification. So in experiment you would find that the increase in temperature would be a lot less.